Hi, good day everyone. Today I'll be presenting about quantum mechanics. Quantum mechanics is a science dealing with the behavior of matter and light on the atomic and subatomic scale. It attempts to describe and account for the properties of molecules and atoms and their constituents, the electrons, protons, neutrons, and other more esoteric particles such as quarks and gluons. In this presentation, I'll be discussing to you first the historical basis of quantum theory, the basic concepts and methods, the interpretation of quantum mechanics, and the application of quantum mechanics. So let's have first the historical basis of quantum theory. Basic considerations. At a fundamental level, both radiation and matter have characteristics of particles and waves. The gradual recognition of scientists that radiation has particle-like properties and that matter has wave-like properties provided the impetus for the development of quantum mechanics. Influenced by Newton, most physicists of the 18th century believed that light consisted of particles which they called corpuscles. From about 1800s, evidence began to accumulate for a wave theory of light. At about this time, Thomas Young showed that if monochromatic light passes through a pair of slits, the two emerging beams interfere, so that a fringe pattern of alternately bright and dark bands appears on a screen, which explained by a wave theory of light. In 1815, a series of experiments by Augustine, John Fresnel, and others showed that when a parallel beam of light passes through a single slit, the emerging beam is no longer parallel but starts to diverge, and this phenomenon is known as diffraction. Early developments. By the end of the 19th century, physicists almost universally accepted the wave theory of light. However, though the ideas of classical physics explain interference and diffraction phenomena relating to the propagation of light, they do not account for the absorption and emission of light. All bodies radiate electromagnetic energy as heat. In fact, a body emits radiation at all wavelengths. Attempts to calculate the energy distribution from the radiation from a black body using classical ideas were unsuccessful, until Max Planck made a bold suggestion. He assumed that the radiation energy is emitted, not continuously, but rather in discrete pockets called quanta. The energy of the quantum is related to the frequency, the quantity now known as Planck's constant. In 1905, Einstein extended Planck's hypothesis to explain the photoelectric effect, which is the emission of electrons by a metal surface when it is irradiated by light or more energetic photons. The kinetic energy of the emitted electrons depends on the frequency of the radiation, not on its intensity. For a given metal, there is a threshold frequency below which no electrons are emitted. Furthermore, emission takes place as soon as the light shines on the surface. There is no detectable delay. Einstein showed that these results can be explained by two assumptions: that the light is composed of corpuscles or photons, the energy of which is given by Planck's relationship, and that an atom in the metal can absorb either a whole photon or nothing. Part of the energy of the absorbed photon frees an electron, which requires a fixed energy known as the work function of the metal. The rest is converted into kinetic energy of the emitted electron. Bohr's theory of the atom. A major contribution to the subject was made by Niels Bohr, who applied the quantum hypothesis to atomic spectra. Bohr's theory has two most important features that survived in present-day quantum mechanics. They are 1. The existence of stationary, non-radiating states, and 2. The relationships of radiation frequency to the energy difference between the initial and final states in a transition. Prior to Bohr, physicists had thought that the radiation frequency would be the same as the electron's frequency of rotation in an orbit. Soon scientists were faced in the fact that another form of radiation, X-rays, also exhibits both wave and particle properties. Max Born law had shown that crystals can be used as three-dimensional diffraction gratings for X-rays. His technique constituted the fundamental evidence for the wave-like nature of X-rays. In 1922, Arthur Holly Compton showed that X-rays scatter from electrons as if they are particles. Compton performed a series of experiments on the scattering of monochromatic, high-energy X-rays by graphite. To interpret his results, Compton regarded the X-rays photon as a particle that collides and bounces off an electron in the graphite target as though the photon and the electron were a pair of dissimilar billiard balls. Faced with the evidence that electromagnetic radiation has both particle and wave characteristics, Louis Du Bois suggested a great unifying hypothesis in 1924. Du Bois proposed that matter has wave as well as particle properties. He suggested that material particles can behave as waves and that their wavelength is related to the linear momentum of the particle. Basic concepts and methods. Schrödinger's wave mechanics. In 1926, Erwin Schrödinger expressed Du Bois' hypothesis concerning the wave behavior of matter in a mathematical form that is adaptable to a variety of physical problems without any arbitrary assumptions. He was guided by a mathematical formulation of optics, in which the straight line propagation of light rays can be derived from wave motion when the wavelength is small compared to the dimensions of the apparatus employed. In the same way, Schrödinger set out to find a wave equation for matter that would give particle-like propagation when the wavelength becomes comparatively small. Postulating a wave function that varies with position, Schrödinger replaced momentum in the above energy equation with a differential operator that embodied the de Broglie relation. He then showed that wave function satisfies the partial differential equation. And this is the time-independent Schrödinger wave equation, which established quantum mechanics in a widely applicable form. An important advantage of Schrödinger's theory is that no further arbitrary quantum conditions need to be postulated. The required quantum results follow from certain reasonable restrictions placed on the wave function. For example, that it should not become infinitely large at large distances from the center of the potential. Thus, the concept of the electron as a point particle moving in a well-defined path around the nucleus is replaced in wave mechanics by clouds that describe the probable locations of electrons in different states. Electron spin and antiparticles. In 1928, the English physicist Paul Dirac produced a wave equation for the electron that combined relativity with quantum mechanics. Schrödinger's wave equation does not satisfy the requirements of the special theory of relativity because it is based on a non-relativistic expression for the kinetic energy. The electron spin hypothesis not only provided an explanation for the observed magnetic moment, but also accounted for many other effects in atomic spectroscopy. Every particle described by the Dirac equation has to have a corresponding antiparticle, which differs only in charge. The positron is just such an antiparticle of the negatively charged electron, having the same mass as the latter but a positive charge. The phenomenon of tunneling, which has no counterpart in classical physics, is an important consequence of quantum mechanics. It has many important applications. For example, it describes a type of radioactive decay in which a nucleus emits an alpha particle. The alpha particle is confined before the decay by a potential of the shape. For a given nuclear species, it is possible to measure the energy of the emitted alpha particle and the average lifetime of the nucleus before decay. The lifetime of the nucleus is a measure of the probability of tunneling through the barrier. The shorter the lifetime, the higher the probability. With plausible assumptions about the general form of potential function, it is possible to calculate a relationship between the average lifetime and energy, and that is applicable to all alpha emitters. This theory, which is borne out by experiment, shows that the probability of tunneling, and hence the value of average lifetime, is extremely sensitive to the value of energy. It would be difficult to account for this sensitivity of the average lifetime to the value of energy by any theory other than quantum mechanical tunneling. Axiomatic approach. Although the two Schrödinger equations form an important part of quantum mechanics, it is possible to present the subject in a more general way. Dirac gave an elegant exposition of an axiomatic approach based on observables and states in a classic textbook entitled The Principles of Quantum Mechanics. An observable is anything that can be measured, like energy, position, a component of angular momentum, and so forth. Every observable has a set of states, each state being represented by an algebraic function. With each state is associated a number that gives the result of a measurement of the observable. Incompatible observables. The measurement of two observables with different sets of state functions is quite different situation. Measurement of one observable gives a certain result. The state function after the measurement is, as always, one of the states of that observable. However, it is not a state function for the second observable. Measuring the second observable disturbs the system, and the state of the system is no longer one of the states of the first observable. In general, measuring the first observable again does not produce the same result as the first time. To sum up, both quantities cannot be known at the same time, and the two observables are said to be incompatible. Heisenberg uncertainty principle for position and momentum states that there is a limit to the precision with which the position and the momentum of an object can be measured at the same time. Depending on the experimental conditions, either quantity can be measured as precisely as desired, but the more precisely one of the quantities is measured, the less precisely the other is known. The uncertainty principle is significant only in the atomic scale because of the small value of Planck constant in everyday units. If the position of a microscopic object with a mass of, say, 1 gram is measured with a precision of 10 to negative 6 meter, the uncertainty principle states that its velocity cannot be measured to better than 10 to negative 25 meter per second. Such a limitation is hardly worrisome. However, if an electron is located in an atom about 10 to negative 10 meter across, the principle gives a minimum uncertainty in the velocity of about 10 to 6 meter per second. The application of quantum theory to the interaction between electrons and radiations requires a quantum treatment of Maxwell's field equations which are the foundations of electromagnetism and the relativistic theory of the electron formulated by Dirac. The resulting quantum field theory is known as the quantum electrodynamics, or QED. QED accounts for the behavior and the interaction of electrons, positrons, and photons. It deals with the processes involving the creation of material particles from electromagnetic energy and with the converse processes in which a material particle and its antiparticle annihilate each other and produce energy. The interpretation of quantum mechanics. Although quantum mechanics has been applied to problems in physics with great success, some of its ideas seem strange. A few of their applications are considered here. Number 1. Electron, wave, or particle. Young's experiment shows both the wave and particle properties of the electron. The wave property predicts the probability of direction of travel before the electron is detected. On the other hand, the fact that the electron is detected in a particular place shows that it has particle properties. Therefore, the answer to the question whether the electron is a wave or a particle is that it is neither. It is an object exhibiting either wave or particle properties, depending on the type of measurement that is made on it. In other words, one cannot talk about the intrinsic properties of an electron. Instead, one must consider the properties of the electron and measuring apparatus together. A fundamental concept in quantum mechanics is that of randomness or indeterminacy. In general, the theory predicts only the probability of a certain result. Many eminent physicists, including Einstein, have not accepted this indeterminacy. They have rejected the notion that the nuclei were initially in the identical state. Instead, they postulated that there must be some other property presently unknown but existing nonetheless, that is different from the two nuclei. This type of unknown property is termed as a hidden variable. If it existed, it would restore determinacy in physics. But according to the Copenhagen interpretation, indeterminacy observed in nature is fundamental and does not reflect the inadequacy in present scientific knowledge. One should therefore accept the indeterminacy without trying to explain it and see what consequences come from it. Paradox of Einstein, Podolsky, and Rosen. Einstein and two other physicists in the United States, Boris Podolsky and Nathan Rosen, analyzed a thought experiment to measure position and momentum in a pair of interacting systems. Employing conventional quantum mechanics, they obtained some startling results, which led them to conclude the theory does not give a complete description of physical reality. Their results, which are so peculiar as to seem paradoxical, are based on impeccable reasoning. They concluded that a correct theory would contain some hidden variable feature that would restore the determinism of classical physics. Measurement of quantum mechanics. The way quantum mechanics treats the process of measurement has caused considerable debate. In axiomatic approach, a measurement changes the wave function abruptly and discontinuously, while in the Copenhagen interpretation of the measurement process is essentially pragmatic. It distinguishes between microscopic quantum systems and macroscopic measuring instruments. On the other hand, the Schrödinger equation is known to apply only to relatively simple systems. It is an innermost extrapolation to assume that the same equation applies to the large and the complex system of a classical measuring device. Many worlds interpretation proposed by Hugh Everett III in 1957, which suggests that when a measurement is made for a system in which the wave function is a mixture of states, the universe branches into a number of non-interacting universes. Each of the possible outcomes of the measurement occurs, but in a different universe. Applications of quantum mechanics. As has been noted, quantum mechanics has been enormously successful in explaining microscopic phenomena in all branches of physics. The three phenomena described in this presentation are examples that demonstrate the quintessence of the theory. 1. The decay of kaon. The kaon, discovered in 1947, is produced in high-energy collisions between nuclei and other particles. It has zero electric charge, and its mass is about one-half the mass of the proton. It is unstable and, once formed, rapidly decays in either 2 or 3 pi mesons. The average lifetime of the kaon is about 10 to negative 10 seconds. Number 2 is the cesium clock. 2. The cesium clock. It is the most accurate type of clock yet developed. This device makes use of transitions between the spin states of the cesium nucleus and produces a wave frequency which is so regular that it has been adopted for establishing the time standard. Number 3. Quantum voltage standard. Quantum theory has been used to establish a voltage standard, and this standard has proven to be extraordinarily accurate and consistent from laboratory to laboratory. So that's all about my presentation. I'm Eula Jade Malakad. Thank you for listening. God bless us all.